Let's be honest, for a lot of us engineers, modal analysis can feel like a bit of a black box, right? You feed your model in, the solver does its thing, and it spits out a list of frequencies. But what do those numbers really mean for your design? Well, today we're going to pry open that black box. The goal here is to build a real intuitive feel for this stuff so you can use these results to make smarter, safer, and just better design decisions. Let's dive in. And we have to start here. This is the big one, the Tacoma Narrows Bridge, one of the most famous, or maybe infamous, engineering failures ever. What you're watching is the catastrophic power of resonance. A pretty small, steady force, in this case just the wind, happened to match one of the bridge's natural frequencies. And those vibrations just amplified and amplified until the entire structure literally tore itself apart.
So that, of course, begs the question for every single one of us in this field. How do we make sure this never, ever happens again? Well, the answer is a really powerful predictive tool. It lets us see a structure's built-in vibrational DNA before a single piece of steel is ever cut. And that tool, as you've guessed, is modal analysis.
So here's our game plan. First, we'll nail down why resonance is so dangerous. Then, we're going to peek under the hood at the math behind it all, the eigenvalue problem. Now, the biggest chunk of our time will be spent right here, decoding the outputs from your software, turning all those numbers into real, actionable insights. After that, we'll see how these results are the foundation for a ton of other analyses, and we'll wrap it all up with some best practices and a super simple 3-point sanity check you should use on every single model.
Okay, so here's the absolute key concept. Every single object in the universe, whether it's a tiny guitar string or a massive skyscraper, has a set of natural frequencies. These are the specific frequencies at which it just wants to vibrate. It's its personality. Now, when an outside force, like an engine running or wind blowing, lines up with one of those natural frequencies, that's when you get resonance. The vibrations stack on top of each other, and the movement can become way, way bigger than you'd ever expect.
So how in the world do we predict what these secret frequencies are? We have to learn to speak the language of vibration. And don't worry, we are not about to get lost in a sea of abstract theory. Just think of this as the fundamental grammar that our FEA solvers use to describe a structure's unique dynamic fingerprint.
And this equation, this is the heart of it all. It's known as the generalized eigenvalue problem. And what it's really describing is this perfect dance, a perfect balance between a structure's internal springiness, that's the stiffness matrix, K, and its own inertia, which is the mass matrix, M. When we solve this, we get two incredibly important things: the natural frequencies, that's our omega, and the mode shapes, which is phi. It's everything we need. So solving that one equation gives us these two key pieces of information for every single mode. The first one is the eigenvalue. That gives us the natural frequency. It's the when. Think of a guitar string. The eigenvalue tells you its musical note, its pitch. The second thing we get is the eigenvector. This defines the mode shape. It's the how. So for that same guitar string, the eigenvector tells us the actual shape of the vibration. Is it just a simple up and down arc, or is it a more complicated S-curve? That's what the eigenvector tells us.
And this slide right here perfectly connects the dots. The math on the left, that's where we solve for the eigenvector, our phi. And the image on the right, that's what it is. That's what it physically means. A very specific pattern of deformation. In this case, it's the classic first bending mode of a bridge. It's this direct jump from abstract math to physical visual insight that makes modal analysis so incredibly powerful.
All right, enough theory. Now for the most important part. What do we do with the results? You've hit run, you've waited, and now your solver has given you a big table full of numbers. Let's start decoding this stuff and turn it into real engineering decisions.
First things first, the most basic output, natural frequency. Now, your solver is probably going to spit this out as circular frequency in radians per second, but for our purposes, we almost always convert it to hertz, which is just cycles per second. This value, f sub n, that is the number you compare directly against any known vibration sources in your system.
And that brings us to what might be the single most important, most practical rule in all of vibration design. I call it the detuning rule. If you know you have an engine that runs at 60 Hz, you must ensure that none of your structure's important natural frequencies are anywhere near 60 Hz. A safety margin of about 15 to 20% away from that number is standard industry practice. This is non-negotiable.
Okay, next up is the mode shape itself. When you animate this in your software, you are seeing exactly how the structure wants to move at that frequency. And what you're looking for are two things: antinodes, Those are the spots with the biggest movement and usually the highest stress, and nodes, which are points that don't move at all. And this is super useful. Got a sensitive computer chip you need to protect? Well, if you can mount it on a nodal point for the most problematic mode, you've just isolated it. It's that simple.
All right, next is the modal participation factor. This is a big one. It basically tells you how excitable a particular mode is in a given direction. So imagine a mode has a really low frequency, which looks scary. But if that mode is, say, a side-to-side twisting motion and your main source of vibration is straight up and down, well, that mode might have a really low participation factor in the vertical direction. A vertical shake might not even get it to move. This is absolutely essential for things like seismic analysis or vehicle dynamics, where you know which way the shaking is coming from.
So this leads to a common question. How many modes do you actually need to calculate? You definitely don't need all of them. You just need enough to accurately capture the important dynamic behavior. And the industry standard for this is the 90% rule. It says that the modes you've solved for must account for at least 90% of your structure's total effective mass in each direction you care about. If you don't hit this target, any other dynamic analyses you run downstream is going to be wrong. Simple as that.
And this chart shows you exactly how that works. See how with each mode we add, we capture a little more of the total dynamic mass. So here, mode 1 by itself only grabs 45%, not even close. We add a couple more, we get to 75, but it actually takes 10 full modes before we finally cross that critical 90% line. Now, and only now, is our model ready for the next step.
And hey, don't just take my word for it. This isn't just some nice guideline. It's a hard requirement that's baked right into the major international engineering codes. If you're doing seismic design, you absolutely have to show that you've met this 90% mass participation rule. It's a matter of compliance and public safety. Strain energy is honestly one of my favorite results to look at. It tells you exactly where the stiffness is coming from for any given mode. It's like an X-ray into your model's weak points. Look at this example. For this mode at 78 Hz, a whopping 82% of the strain energy is concentrated in that little bracket. I mean, what a huge design insight. It's basically screaming at you that if you need to raise this frequency, stiffening that bracket is by far the most efficient way to do it.
Okay, so we know how to read our results. We even know how to use them to make smart design changes. But where do we go from here? It is so important to remember that modal analysis is rarely the final step. Think of it as the essential foundation for a whole bunch of other more advanced dynamic simulations.
This workflow really shows you just how central modal analysis is. All those results we just talked about, the frequencies, the mode shapes, the participation factors, they get used to build a super efficient but still dynamically accurate model of your structure. This trick is called modal superposition, and it's the input for all these other analyses. Whether you're doing a response spectrum for an earthquake or a harmonic analysis for a spinning motor, it all starts right here.
But of course, all of those cool downstream analyses are completely worthless if your initial modal results are junk. We've all heard it. Garbage in, garbage out. So let's quickly cover a few absolutely essential checks to make sure your model is giving you the truth. Okay, 3 key things to check. First, your boundary conditions. A bulletproof way to check your model's basic health is to run a free analysis with 0 constraints. You should get exactly 6 rigid body modes at or very near 0 Hz. If you get more, you've got parts that aren't connected right. If you get fewer, you've accidentally grounded something. Second, mesh convergence. Just make sure your mesh is fine enough to capture the curvy shape of your highest mode of interest. And third, think about pre-stress. If your part is under a heavy load while it's operating, that stress changes its stiffness, which will change its natural frequencies.
Wow, we have covered a lot of ground. So let's wrap this all up. Let's distill everything down into a simple 3-point sanity check that you should do after every single modal analysis you run. This is your final gut check before you sign off on the results.
Here it is. Number 1. Are your frequencies safely away from your known excitation sources? That's the detuning rule. Number 2. Have you hit that 90% cumulative mass participation in all the important directions? And number 3, this one is huge. Animate the modes. Just watch them. Do they look real? Do they make physical sense? Or do you see some weird localized flapping that's probably just a modeling error? If you can give a confident yes to all 3 of these, you're in good shape.
So, I'll leave you with a final thought and a little challenge. Go find the last model you were working on. Strip off all the constraints, all the boundary conditions, and run a free modal analysis. Can you find them? Those first 6 rigid body modes, 3 translations, 3 rotations, all sitting there right around 0 Hz.
It is the single best first step you can take to build confidence in your dynamic models. Give it a shot. Thanks for watching.